Nowadays, seeing robotic arms doing work is the norm. But how do we control their position? We can write the problem using mathematics, so let's figure it out together. As a simplified situation, let's consider a double-jointed mechanical arm moving in the xy plane. And in particular, we want to position the end effector, the tip of the arm, on a target point. Or in other words, we want to minimize the distance between the tip and the target point. From a mathematical point of view, this is a minimization problem, and it consists in finding the lowest value of a given function, typically called cost function. As we said, we consider the mechanical arm moving in the xy plane with the base fixed at the origin of the axis. So let's define its geometry. We have two joint segments having a fixed length L1 and L2. And θ1 and θ2 are the two angles of the first and second segment relative to the x-axis, respectively. Our target is the orange star, which has coordinate xp, yp, and the point xy is the position of the tip of the arm, which depends only on the angles θ1 and θ2. Using some trigonometry, we can project the arms on the x and y axis, obtaining these expressions for the tip position. Now let us write the distance between the tip and the target point xp, yp in terms of the angles θ1 and θ2. We are now ready to formulate the minimization problem. We want to find the joint angles θ1 and θ2 that minimize the distance dp positioning the tip closest to the desired target. Equivalently, we can also minimize the square of this distance, setting the cost function j equal to dp squared. So before solving the problem, let's have a look at the function j. It can be represented as a surface in the space R3. On the two horizontal axes, we have the angles θ1 and θ2 in radians, while the value of the square distance, j, is reported on the vertical one. Our goal is to identify the two angles θ1 star, θ2 star that are associated to the minimum point, the star. Those angles are the ones that bring the tip closest to the desired target point. And the question is, how can we find them? We will use a popular numerical algorithm called the gradient descent method. So let us briefly explain how it works. So our goal is to reach the lowest point. Intuitively, the gradient descent method starts from an initial guess and builds a sequence of solutions that gradually approaches the minimum. So we want to descend as fast as possible. So how can we choose the best directions? To answer, let us plot the level curves connecting points at the same elevation. And let us plot the gradient of the function j given by this expression. And as you can see, at each point it is a vector, and the opposite of these vectors guarantee the steepest descent. Now we need to do some computation. So since j depends on x and y, which in turn depends on the angles, we use the chain rule to get this formula where the factors are given by these expressions. And putting everything together, we finally have the expression for the gradient, which is the main ingredient of the method. Here's what the algorithm looks like. Starting from an initial guess, θ1 0, θ2 0, we perform iteration counted with an index I, and at each iteration, we build a new approximation of the angles with this formula where alpha is a positive number called learning rate or step length, and it determines the length of the step in the direction opposite to the gradient. We stop the computation when j is small enough. Say it is smaller than a tolerance that we decided in advance. And this means that the distance between the tip and the target is small. And also note that the iterations stop anyway if the maximum number of iterations is exceeded. Now we just need a computer code to perform all these operations automatically, and in the next videos we will learn how to write it.